In this section we're going to look at bonding, and we're going to look first of all why chemical bonds form. So we know that they form because what happens is it's to do with the outer electron arrangement of the atoms, and when they bond together they either share or they transfer electrons from one atom to another. Now at GCSE you were taught there were three main types of strong chemical bonds. They're ionic, covalent and metallic. And what you need to know about ionic bonding at A level is be able to show why ions form, look at properties of ionically bonded compounds and describe the structure of ionically bonded compounds. But what we're going to do first is we're going to look at how do we decide if a bond is going to be ionic, covalent or metallic. To get a better idea of bonding at A level, it's best first of all to look at this concept of something called electronegativity. Here's the definition of electronegativity and make sure you learn it. So electronegativity is the power of an atom within a covalent bond to draw an electron pair or electron density towards itself. As I come to explain it, it will become apparent, it will be easier to memorise this definition. So here's a little snippet of the periodic table. So a chemist called Linus Pauling decided on a value and assigned it this value for electronegativity. So notice that fluorine has the highest electronegativity in period 2. And electronegativity, as you see, increases in steps of 0.5. Notice as you go down group 7 here, electronegativity decreases. So we've just been looking at ionisation energies, and therefore the two are linked. As you go across the periodic table, the nuclear charge increases, and so does electronegativity. So the greater the nuclear charge, the greater the electronegativity. As you go down a group, the shielding increases, and so does the distance from the nucleus, and therefore electronegativity decreases as the outer electron that would form bonds gets further away from the nucleus. Also, the smaller the atom, so if you look here, lithium is much smaller than sodium, the closer the nucleus is to the outermost electron. So the larger the nuclear charge or the shielding effect, so the less shielding there is, the greater the electronegativity. So fluorine is the most electronegative element in the periodic table. Notice also that the noble gases do not have a electronegativity value, and that's because they don't form covalent bonds, because the definition is the power of an atom within a covalent bond to draw an electron pair towards itself. Here is a simple what's called Lewis dot cross structure of a covalently bonded fluorine molecule. The pair of electrons here are shared between the two fluorine atoms. At the centre of each fluorine atom is a fluorine nucleus, and both fluorine nuclei have 9 protons each. Those 9 protons attract all of the electrons, including this pair of electrons, in the covalent bond. This pair of electrons is going to be equally attracted to this nucleus and also to this nucleus. This electron pair here isn't just sandwiched between the two fluorine nuclei. All of the electrons within the fluorine molecule in the outermost shell would be orbiting around those two fluorine nuclei. And this shows the electron density. So we can actually carry out an electron density map similar to that of a contour map in geography. So the density here, this shaded purple area, is where you might find that pair of outer electrons. And you can see here that the electron density is equally shared because both fluorine nuclei have got an equal attraction for each of these fluorine atoms. If we look at a molecule of hydrogen fluoride, however, hydrogen here has got 1 proton in its nucleus, and whilst its outermost electron is right next to the nucleus because there is no shielding, fluorine has got 9 protons in its nucleus. So fluorine has the greater effective nuclear charge. We can imagine that fluorine's nucleus has got more pulling power, that the electron the electron density is going to be closer to the fluorine atom. So if we look at an electron density map of hydrogen fluoride, because fluorine has a greater pulling power or electronegativity, the electron density is going to be greater around the fluorine atom. So it's more electronegative, so within a covalent bond it's attracting the electron density towards itself. So let's look at the difference in electronegativity. Fluorine has got a value of 4.0 and another fluorine atom has a value of 4.0. So delta E, which is the difference in electronegativity, is 4, take away 4, which is 0. So there's no difference in electronegativity, so we say that those electrons are equally shared. But if we look at hydrogen fluoride, hydrogen here has an electronegativity of 2.1 and fluorine has an electronegativity value of 4. So this time the difference in electronegativity is 4 take away 2.1, which is equal to because the nucleus of fluorine is much less shielded, as you can see here, it's in the 2p subshell, and its electronegativity is 4. If it's close to a sodium atom whose electronegativity value is only 0.9, and you can see here this outer electron is much less shielded, the pulling power of the fluorine nucleus is so great that it doesn't share the electron actually gets transferred to the fluorine atom. This time, ions are formed, not a molecule, and complete electron transfer happened so that sodium now becomes a sodium ion with a positive charge, and this 3s electron has moved over to the 2p subshell of the fluorine atom, which becomes a fluoride ion. This time the difference in electronegativity is 3.1 and an ionic bond is formed. So remember, the ionic bond is the electrostatic force of attraction between oppositely charged ions. There is no sharing of electrons. So, as a rule of thumb, when there is a small difference in electronegativity, you're going to get covalent bonds. When there's a large difference in electronegativity, you're going to get ionic bonds. So at GCSE, you were taught that if a metal atom, here's your metals on this side of the periodic table, reacts with a non-metal atom, you're going to get ionic bonding. And when you've got a non-metal reacting with a non-metal, you tend to get covalent bonding. And that still stands. A covalent bond is two non-metal atoms with an electronegativity difference less than 1.9. An ionic bond is formed when there's a metal and a non-metal atom with an electronegativity difference greater than 1.9. And a metallic bond is simply two metals bonding together to form a giant lattice with a sea of delocalized electrons. So what we're going to do now is look at some differences in electronegativity values and decide if they're ionic or covalent. Here's sodium chloride, sodium and chlorine. The electronegativity value of sodium is 0.9. The electronegativity value of chlorine is 3. The difference in electronegativity is 3 take away 0.9, which is 1.9. And therefore we say it's ionic because its electronegativity value is 1.9 or greater. Let's look at the others. Can you do this and then check your answers by moving the video on? So we decided that sodium chloride was ionic because the difference in electronegativity was 1.9. Now let's look at hydrogen and chlorine to make hydrogen chloride. Hydrogen's electronegativity is 2.1 and chlorine's is 3. So the difference in electronegativity is 0.9 and therefore it's a covalent bond because it's less than 1.9. Let's have a look at hydrogen and oxygen. Hydrogen's electronegativity is 2.1, oxygen's is 3.5, the difference is 1.4 and therefore it's still covalent because it's below 1.9. Sodium and hydrogen. Now you might think that this is going to be ionic because it's a metal and a non-metal. However, the difference in electronegativity is 1.2 and we'll come back to compounds like this in the next part of the video. Silicon and oxygen. Oxygen is 3.5, silicon is 2.5. The difference is 1, which is less than 1.9, so it's covalent. Here we've got two metal atoms and therefore it's going to be metallic, even though the difference in electronegativity will be 0. Carbon and sulfur. Carbon's electronegativity, as you can see here, is 2.5 and so is sulfur's. And therefore the electronegativity difference is 0. It's a covalent bond. Try potassium and fluorine. Potassium's not on our table here, but we're going to predict it's lower than sodium's. So we'll say it's about 0.8. Fluorine is 4. Definitely ionic because there is a big difference in electronegativity. So at GCSE you were taught that a bond can either be ionic, covalent or metallic. Well, in fact, it's slightly more complicated than that. What we have, in fact, is a spectrum of pure covalent bonds to the other end of the spectrum, which are pure, perfectly ionic bonds. But in between, we have some bonds which are said to be polar covalent. They have some slight ionic character. And these are represented by these little symbols here, delta minus and delta plus. So first of all, let's have a look at what the definition of a covalent bond is. So definition of a covalent bond is the sharing of a pair of electrons between two atoms. A polar covalent bond is the unequal sharing of a pair of electrons between two atoms. So the electrons forming the bond are unequally distributed. And this is when you have a difference in electronegativity, which is in fact less than 1.9. So it's not ionic, but it's greater than 0.4. So there's the definition again. Make sure you learn this off by heart. A polar bond is a covalent bond between two atoms where the electrons forming the bond are unequally distributed, represented by delta minus and delta plus, where the electron distribution favours the more electronegative atom, and therefore the electrons within the bond tend to congregate or be pulled towards the most electronegative atom. So let's have a look at some covalently bonded molecules here and decide, are they pure covalent or dated, or pure covalent or polar covalent. So here are those covalent bonds again. If you've got two non-metal atoms with the same electronegativity, obviously the difference in electronegativity is 0, so that's going to be a pure non-polar covalent bond. But here, when hydrogen bonds with nitrogen, the difference in electronegativity is now 0.9, and that is definitely a polar covalent bond. Hydrogen and carbon is on the brink. It's 0.4, which is 0.4, so we would say that carbon-hydrogen bond is non-polar. Fluorine bonding with fluorine, again the difference in electronegativity is 0. That is a pure non-polar covalent bond. But here, look at hydrogen and fluorine. The difference in electronegativity is 1.9. You could almost assume it's ionic. However, the small size of the hydrogen atom and the fact that the electron is the pair of electrons is next to the nucleus means that the fluorine doesn't have the pulling power to completely remove that electron. So hydrogen-fluorine bond is really, really polar covalent. Again, with hydrogen and oxygen, the difference in electronegativity is much greater than 0.4, and therefore this is also a polar covalent bond. So if we were to look at that spectrum again, where we said there are pure covalent bonds, there are also pure ionic bonds, but there are ionic compounds with covalent character. And you can see here, if we've got a very polarizing lithium atom and we divide its size by its charge and we get a size-charge ratio, we refer to this very small ion here as very polarizing. The bromide ion, because of its large size, the outer electron cloud can become distorted and be pulled towards the small lithium ion. So we're tending to get some electrons appearing between the two ions, which is some covalent character. And we say that the bromine or the bromide ion is very polarizable. And if we look at the difference in electronegativity between lithium and bromine, you can see that it's less than 1.9. So even though we have a metal bonding with a non-metal, we have a relatively small difference in electronegativity for an ionic compound, and we therefore say that lithium bromide is ionic with covalent character. Here are some ionic radii. It's really interesting to notice what happens as you go from left to right across the periodic table. The cations, for example here Li plus and Be2 plus, can you see that the radius decreases as the charge on the ion increases? So if we look at aluminium here, aluminium with its very high charge and its small size is going to be highly polarizing compared to rubidium, which has got only a single positive charge, a much larger radius. Rubidium ions are going to be not polarizing. So it therefore follows that compounds that contain aluminium are going to have a lot of covalent character. So let's look at aluminium fluoride. The difference in electronegativity between aluminium and fluorine is 4, take away 1.5, which is 2.5. So therefore we can predict that aluminium fluoride definitely has ionic bonding. But let's now look at aluminium bromide. The bromide ion is much more polarizable and the electronegativity difference is less than 1.9. And therefore aluminium bromide is in fact covalent. So let's remind ourselves about the charge size ratio. Let's compare aluminium ions with potassium ions. Aluminium ions have a charge of +3, potassium ions have a charge of +1. If we now go to the size of the ionic radius, aluminium's is 53.5 nanometers, whereas potassium's ionic radius is 138 nanometers. So now, if we look at the difference in the polarizing power, i.e. the charge divided by the size ratio, you can see in terms of magnitude how much bigger aluminium's is to potassium's. In fact, aluminium's polarizing power is 8 times that of potassium's. So if you divide 5.6 times 10 to the minus 2 by 0.7, times 10 to minus 2, you'll find that the polarising power of aluminium is 8 times greater. And therefore, compounds with aluminium that have aluminium and larger anions tend to have highly covalent character.